Okay, the Kaplan-Meier survival curve estimation. So this Kaplan-Meier thing is to estimate the survival curve. So if we're going to get anywhere, we have to know what survival curve is. The chart, the plot gives us the survival probabilities over time. We can use the chart to see that an individual survived to at least time t with a blah 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 probability. Okay, for this example we're looking at let's see, cancer data. So what I've got is, this is what it typically looks like. We've got time to the event, in this case time to death. Then we've got a factor. You don't need to have this, but we do here because we have an experiment where patients are divided up and given one of 4 levels of treatment, being drug A, B, C, and then a placebo. And then we have a status variable. This is very interesting because the status variable tells us whether or not the time recorded for individual is the time of death, or that was the last time we saw the person alive. But we don't know whether the person, but we just know that person was still alive at that time, but we don't know the actual time of death. So this is like the censoring variable. So it's coded 1 if the time recorded is actually the time to death, and 0 otherwise. So if we look at the case 1 here, death at time 4, we don't know what the units are. It could be months, it could be years. And the status is 1, so that the time recorded for that individual 1 is actually the time of death. Whereas for case 6, the time, just coincidentally, is also 6, but this is coded 0 for status. So at the time 6, we just know the person was still alive, but we don't know the real time of death. So what's good about this procedure is that it takes then account of censoring. This is what we call censoring, where we just know that the person is still alive, but we don't really know the time of real time of death. So there are 2 questions with this analysis. One is get the survival estimate of the survival curve and interpret it. And then the second thing we can do is that we can get survival curves for different levels of a given factor, here being drugs A, B, C, and then the placebo. And then the question is there difference between the survival curves? So let's do the first thing. Okay, get the curve. That's actually quite easy in SPSS. Analyze survival, Kaplan-Meier. Something I filled out already. Let's reset it because I've cheated. Okay, time, put into the time box. If you didn't call it time, if you call it something else like duration or whatever, just put that in the time box. It's the thing that it's the time to the event. Treatment, if you have it, that's a factor. If you have a factor. If you don't, then just leave it blank. And then the status here, which you need because probably you have censoring going on, put it in here. I've got to complete this because it says define the event. So the event is the actual time to death. We've coded it 1. Alright. So I put 1 in that box. Continue. The whole of other options, but we don't need them like strata or anything like that. That's for more kind of advanced cases. Now we can go on here because since we have a factor and we've got 4 levels of that factor, we want to be able to compare. See, part 2 of the analysis, we're doing it all in one here. Why not? We want to compare the survival curves, so we go here, compare factor, and here you got test statistic, and I'll tell you what these tell us in a moment, but for now let's just click on them all, forget everything below there, go continue. So we clicked on log rank, Breslow and Terenware, and at this stage we can click OK, but let's just look at some of these other things. What's in the options? It gives us statistics, survival tables. Yes, that would be a good idea if you want confidence intervals of time of death and such like. Mean and median survival times, yes, if you want to report those. Quartiles, if you want them. Okay, plots, survival plot would be good, so let's click that. We can also get the hazard plot, but we want the survival plot, that's what this is about. If you want to save any of the output, click save, and you can save the actual estimates of the survival or the standard error of the survival. Okay, well, you don't need to do that, and then we'll click OK. Right, let's see what we've got. We've got number of tables. As usual with SPSS, it dumps out a whole load of stuff. First table, we've got a summary of the data. So treatment, that's the factor, as told you, in 4 levels: drug A, B, C, and the placebo. And we've told that we've got 30 individuals in each level. So this is what we call, if you think about ANOVA analysis, this is what we call a balanced design. And if you think about ANOVA analysis, this would be, if we're doing ANOVA analysis, this would be a one-way between ANOVA, one way between ANOVA. Yep. Okay, and number of events, these are the actual number of deaths then. So 25 out of 30 people died, and the remaining were censored. So we don't know what happened to them. They were just alive at the time we last saw them. Okay, so censoring, that's the percentage that's censored. So for drug A, about almost going up to 17% was censored. Most people were censored in the placebo group, 30%. So around, just slightly under double the other ones. Censoring percentages for drugs A to C are identical. Okay, then we can look at next down here the survival table. So what we've got here, and this is just a table, it's not, we actually use the numbers here to create the chart. The drug A, the first instance of death was at time 1, and it was real because its status is 1, so that's real actual death. Estimate of the survival then is 0.933, and with a standard error. Then the next table, we have the table of mean and medians of survival times for each of the levels of the factor, estimates along with confidence intervals. So if we're looking at, and we've got for mean, and then we've got a block for median, so it depends on, it's your choice, which one do you want to look at. Now, which one you look at really depends on the distribution of those times of death. So naughty me at the start, it would have been a brilliant idea if I'd plotted something like a box plot of the time of deaths for each of these guys. So let's do it at the end. But to be honest, I already ran this through before I came to talk to you, so I already know that the median is better because all these guys are skewed, positively skewed. So in which case I'd be more interested in the median. And then if we look at the 95% confidence interval of the time of deaths across the 4 levels of that factor, we can see that they overlap through about there 3.5 to 10. Next one is for level drug B is about 7 to 12, which overlaps with drug A, which overlaps with drug C. God, I hate this double click to activate thing. And then placebo 5.6 to 10, so they all overlap, suggesting there's no difference in the actual median value. Right, next let's go to the survival function. Okay, this is actually where I want to get to really for round 1. So that table I showed you earlier about probabilities, here it is in a graph, and we've got 1, 2, 3, 4 survival curves because there's one for each level of the factor. So in blue here, this is drug A. Drug B is in green. Slightly lighter color is C, and then this purple one is placebo. If we just look at the time, so everybody here basically starts out alive. So you can see cumulative survival is basically a probability, so it's between 0 and 1. So everybody at the start is alive, so that's why the cumulative probability is 1. The probability that you're alive to at least time 0 is 1. Okay, and then the first instance when everybody's all gone is for placebo, and that is just a time a shade over 10. That's for placebo group, they've all kind of passed away. And then next is drug C and B, they pass away around 20. And then for the let's see, this drug A, it's more towards 50. So you can see that the survival curve drops down and in steps as with time. Every time there's a step drop, that means an event or events have happened, so there's been at least one death. So we can see from here that the time to last death, if you're on the placebo, was around this time, about 11 or 12. And for the final death here for the drug A, you're talking about closer to 48. And those times, the exact times, we can get from the table earlier. Where you see crosses, where we've had censoring. So some of these individuals were recorded being alive at that time, but we don't know the actual time of death. So if you see crosses, that means there's censoring in that level. No crosses means that no censoring occurred. We know from the data, from the summary stats, that there's censoring going on in all of them. So going back to the tables here, that's the survival table. This is where you dig up those probabilities, and censoring. We know that they've all had censoring going on. Okay, finally then, the second question is that now that we've got this and we've got an idea of what this survival curve looks like, question is the difference between the survival curves? Well, let's just say that, just emphasize again that these survival curves, they're estimates, right? So in other words, they're guesses of the population survival curves for each of the groups. What I mean by estimate is that, yeah, these are guesses. So if we were to get another 30 bunch of people and put them in group A, another randomly chosen from B, randomly chosen for C, and randomly chosen for placebo, 30 in each group, like before, and redid this trial, you will find that the estimates, these lines will be slightly different because they are estimates, because they're different people, numbers are going to be slightly different. But the idea is that these people are supposed to kind of be representative of the population, so those curves should be similar to this curve, and in turn this curve should be similar to the population, the true curve. The question is now then, is there a difference between the survival curves? Now that's an interesting question, because if there is no difference, I mean, you look by eye and you might think, oh, there is, look at that, it's obviously a difference, look at how far drug A is to all the rest, but we need a formal test. Say we ran the test and we say that there is no difference in any of these survival curves, then that means that there's actually no impact of the treatment on the individuals. Okay, so let's do the test. Right, just recall that for any test we have a null hypothesis and the alternative, or otherwise known as the experimental hypothesis. There are three versions of this test, and let's just state the null now. The null, and it's just like for ANOVA, the null is that there is no difference in the survival functions or survival curves for the levels of the factor treatment. Another way of saying it more layman terms is like all the survival functions are the same for the different treatments. Okay, right, so here we go. I'll just tell you what the tests are. Log rank, and then there's this generalized Wilcoxon, and then Taron-Ware, which we've called upon. We call all three of them. They're chi-square tests. We're interested in looking at the significance, otherwise known as the p-value, for corresponding for the tests. Recall the rule: if the p is low, say below 0.05, you reject the null. So the log rank test statistic is 3.5, 3 degree of freedom, but more importantly, the associated p-value is 0.312, way bigger than 0.05, so we do not reject the null. The generalized Wilcoxon, all these are the same null hypothesis, so generalized Wilcoxon, the p-value is way higher than the log rank, it's about 0.67, so we do not reject the null. Taron-Ware, p-value 0.55, do not reject the null. So all three of them agree. And you'll hear it said that these three give similar results, so unless your lecturer, your professor is inclined to use that you use one of them more than the others, then just do as you're asked. But if we think about how these work in a very similar way. The log rank places more emphasis on events happening later in time, whereas this generalized Euler-Coxon places more emphasis on events or deaths here happening, number of events that happen early in time. And this theorem where is like in the between the two. That kind of explains now. By the way, you can shut your ears if you don't want to hear this bit. That kind of explains. I'm going to explain why this p-value is way lower than these two. That explains why this log rank p-value is like way below these two. It's going more towards, rejecting, isn't it? Because it's getting small. Why is that? Because if we look at the survival curves here, that log rank test places more emphasis on events happening further in time. So since for drug A you've got something happening way out here, it places quite a lot of emphasis on that, and that's why it's pointing more towards that there is evidence to reject the null, but it's not small enough. Anyway, the thing is that these three things tend to say the same thing, and all three testing the null, that there's no difference in survival curve across the levels. And when I say survival curves, I'm not saying estimated survival curves, I'm talking about population survival curve, the true survival curves. Now, if you want the confidence intervals around these guys here, I don't know there's a quick way to do this in SPSS. I think you have to construct those confidence intervals using a formula and then draw it. If you want confidence intervals around these guys, I suggest you use R, which is way faster. It's very convenient, and I've shown you how to do that in the R video. So R is another package, that's a huge package that popular among biostatisticians. Okay, to tie up the loose ends then, talked about what survival function is, talked about how to test the difference of survival functions across the levels of a factor. Final things, let's go back to talk about why we would report the median rather than the mean. Okay, so we'll go to analyze and want to kind of explore our data, and what we want is time independent list treatment in the factor list, and we want to go plots, and I want box plots. Then that's all I want. Okay, so I just choose here plots. Okay, right, recall this from ANOVA analysis. So we've got the dependent variable time here, and we've got the levels of our factor going across here. You can see that these boxes suggest that they are pretty much no difference because they're overlapping, and moreover that's kind of skewed, isn't it? They're skewed. And here you'd call these guys probably outliers or something like that. Like, look at that. That's because some of these guys, time to death, they're lucky. They lived a lot longer than the rest of the people in their group. So this 12 here, way out towards 50. If we look at our survival curve, here's for group A, is way out here. Okay, but emphasize that ANOVA analysis is not the same as survival analysis. ANOVA analysis is addressing different question. It's comparing differences in means, whereas in survival analysis we are focused on looking and comparing the survival function. If the survival functions, then that means the populations across the levels are exactly the same, so the distribution will be the same. That being the case, the means, variances, everything have to be the same, in which case they must have the same mean, and then if you did analysis of variance, you'd find that means are the same. Okay, so I think that's about it. Yep. So the next step after this, KM, is to look at the Cox proportional hazard model, which we're able to kind of model the impact of various things on the survival time, because here we've only got the factor, but we've not been able to include continuous things like A. Okay, that's all. Cheers.